Hey guys, welcome back to chapter 14. In this video, we are going to work another example of a weak, but this time we're going to move on to a weak base. So these, again, bases should start like throwing up red flags in your brain. There's going to be an extra step or a twist or something funky about them. So just be on the lookout for bases. They tend to cause a little extra work. So here's our problem. We want to find the pH of a 0.0015 molar morphine solution. Okay, so this question's on a test, and it doesn't have the heading weak base. So how do you know? Well, first, I probably write it somewhere in there. So the weak base morphine, what is the pH of it? So I might write it in the title. Another good indication is there will be a K value given. And in this case, it's the KB value. And so that automatically tells you KB, B for base. We know that's going to be a weak base. Okay. The other twist with bases is that they tend to have formulas that are really, really long. So let me show you kind of a tip, trick, tool that you can use. You certainly are welcome to look up the chemical formula for morphine and use that in writing your chemical equation. But if that's not something you want to do and instead you want to just get comfortable with this generic formula, that might be a better path to take. So I will tell you, if you want to know it, morphine is C17H19NO3. So if you want to use that, by all means, go ahead. What I would do is I would use this generic B for base. So that's going to be our weak base. And just like we did with acids, we're going to mix it with water. So in this case, base is our proton acceptor. So on the other side, it's going to accept that proton. It's going to be HB. Go plus. And then water in this case is acting as our acid, so it donates its proton, and so instead of having two hydrogens, it's just going to have one, and that's where we see that hydroxide. Okay. Once we have this on the paper, it's a weak base, right? It's an equilibrium problem. So again, one of the first things we're going to want to do is go ahead and draw our ice table. In our ice table, we're going to have our reactants, so B for base. We do not include water because it's a liquid. Our product, HB, and hydroxide. Before we get too deep into this problem, I do want to talk about, well, what's the purpose of this exercise? So when we were solving for pH of a weak acid, hydronium was our target. But in this case, we don't have hydronium, but we do have hydroxide. So if I can get to the equilibrium concentration of hydroxide, what can I then do with that? Yeah, I can get to POH and then get to pH. So the purpose of this exercise is going to be ultimately to solve for the concentration of hydroxide. And then after we do that, we can take that to solve for pH. Okay. All right, so our initial values, it gives us that the concentration of the weak base was 0.0015. We did not have any of our conjugate acid. We did not have any hydroxide. Now we're going to put the change in. So the only one way for our products to go, and that is up, which means our reactant has to go down. So at equilibrium, our products are going to be X, and our reactant. Go ahead and draw that on an angle because it got kind of tight in there. So from here, we are going to set up our K equation, so B for base. It's going to be our products, which are HB plus and hydroxide. Oops. and our reactants. We're given our value for HB, so it's 1.6 times 10 to the negative 6th. And at equilibrium, our reactants are X and X, our products are X, and our reactant is. So again, same chapter, we're still going to make the assumption that X is small is valid. So we get rid of any X's that are added or subtracted. So that's going to clean this up to 1.6 times 10 to the negative 6 equals, condense the top to X squared, and the bottom is just 0.0015. I'm going to click ahead a slide so that I have some room to work here. There we go. All right, so we are here, 1.6 times 10 to the negative 6 equals X squared. So this is where we were. All right, so now I'm going to try to solve for X. So first I'm going to get that out of the denominator. Whatever I do to the right side, I also have to do to the left. So we are going to have X squared, and then I'm going to take 0.0015 times 1.6 times 10 to the negative 6. I have 2.4 times 10 to the negative 9. Then to get X by itself, we're going to take the square root. And second square root, second answer, X equals 4.89. 4.89 times 10 to the negative. All right, we're back to what does this mean? Why did we do this? What was the purpose of the exercise? So remember we had our ICE table. This is just a cleaned up version. We had our ICE table, and we were trying to solve for the concentration of hydroxide. Okay. So X is 4.9 times 10 to the negative 5th. We can also say that the concentration of hydroxide is 4.9 times 10 to the negative 5th molar. Now that we have the hydroxide concentration, we want to get to pH. And as we saw before, there's going to be two paths to get there. So the first path, and likely the one that I think you guys will take, is as follows. So if I have hydroxide concentration, I can then determine the pOH, which is just the negative log of that. So pOH equals negative log of 4.9 times 10 to the negative 5th. And then pH is just going to be 14 minus pOH. So pH equals 14 minus 4.31, 9.69. There is another path to solving this, and you could use that KW equation where the hydroxide concentration times the hydronium concentration equals 1.0 times 10 to the negative 14. So we plug in our hydroxide concentration of 4.9 times 10 to the negative fifth. And we solve for hydronium. So to get hydronium by itself, I'm going to divide by 4.9 times 10 to the negative fifth. Those cancel. We get concentration is 2.04 times 10 to the negative 10th. And then pH equals the negative log of that. And pH equals negative log 2.04 times 10 to the negative 10th. And we get 9.69. So 2 paths to get to the exact same answer. Of course, we always have to ask ourselves, does this make sense? I made the claim that morphine was a weak base, and when we looked at the pH of that solution, it is in fact basic, but not terribly basic, not too far up that pH scale. So bases tend to have some extra steps, some twists and turns along the way, but the more you practice them, the more you'll be prepared for them. I hope you found this helpful.